Hello, here is the introduction about B-Series MCU hardware information. The report will be divided into the following sections. First is the brief introduction, B-Series MCU, which includes RTL8762C, RTL8762D, RTL8762E, RTL8752H, RTL876 and 272G, is an ultra-low power system-on-chip solution for Bluetooth 5 low-energy applications that combines the excellent performance of a leading RF transceiver with a low-power ARM Cortex-M4F and rich powerful supporting features and peripherals, which is suitable for BLE remote controller and other low-power BLE applications. And the MCU cores are popular platforms, which facilitate customers' implementation. For example, here gives the features table of the most common IC type of RTL8762C series, CJ, CJF, CK, CKF etc. Generally, our IC can be divided into two groups, with F such as CJF, CMF, CKF, means that it has an internal flash, no need to add an extra flash IC, and without F such as CJ, CK, which requires an external flash to work. The basic functions have been listed above, such as GPIO, ADC, SPI, UART etc. Besides, the RTL8762C supports an analog mic interface that integrates a Sigma Delta ADC, programmable gain amplifier, 5-band equalizer and microphone bias circuit for voice command application. The RTL8762C embeds an IR transceiver, hardware keyscan, and quad decoder on a single IC, and is provided in a QFN package. And for more details, you can refer to the HDK document and datasheet. Here also gives the features table of RTL876 and 272G, compared to the RTL8762C series. RTL876 and 272G has more types, packages and features. About other series, please refer to the corresponding datasheet and HDK of other series for more detailed information. Then is the introduction about block diagram. The following figure is the RTL8762C simplified IC block diagram. The system includes the ARM Core MCU, RF circuit for BLE, sufficient peripheral interfaces such as GPIO, timer, aux-ADC, audio codec, UART, I2C, SPIR, keyscan etc. The block diagram of RTL8762D/E and RTL8752H is similar, and please refer to corresponding datasheet for detailed difference. The following figure shows the overall block diagram of RTL876 and 272G Bluetooth Low Energy SoC series model. Compared to the previous series, RTL8762G/72G has made several changes and add many new features. The system includes the real M300V MCU, RF circuit for BLE and 2.4 GHz proprietary. Add the new peripheral interfaces such as high-resolution stack, USB 2.0 high-speed/full speed, Ethernet RMII, ISO 7816, A2C, LCD SEG/COM, IDU, PPE, display controller. Here is the example of detailed power architecture figure of RTL8762C and D and E, which are almost same. The HVD pin will connect to the PMU, power manage unit, and an external LC tank to generate VED core, which will supply power to CPU digital core and radio frequency part. The aux-ADC and audio functions are power supplied by the VBAT pin. And the VDDIO pin powers the pad cells. One point to note is that for certain packages such as RTL8762CJ/CK, the HVD pin is combined with VBAT pin to save space. About the work mode of PMU, It support LDO mode and buck mode to generate VED core. Buck mode has higher efficiency to save power, while LDO mode could work without the external inductor to save the BOM cost. User can choose the appropriate mode based on their needs. The system is supplied with 1.8V to 3.3V by a single power source. For more flexibility of peripheral usage, I/O voltage VDDIO can be different from VBAT, but VDDIO should be less than or equal to VBAT. Here shows a simplified power architecture diagram of RTL8752H, same as before. It also has an efficient DC-DC regulator in the PMU that can provide power to the digital core circuit, RF circuit, and clock source. And the DC-DC converter also support two modes, buck mode and LDO mode. When high efficiency is required, the buck mode can be used. And the VDANA and VED core require external capacitors. Additionally, buck mode requires inductor to be placed between the LX1 and LX2 pins. When use LDO mode, the inductor can be replaced by 0 ohm resistor to save cost. Furthermore, VDDANA is used to supply RF power amplifiers and LDO_ANA voltage. VANA is generated by LDO-ANA with a voltage of 1.2 V and is used to supply RF synthesizers and 40 MHz XTAL voltage. VDD core is used to supply power to digital circuits or SRAM and has a power cut at the back end to save power in deep LPS. Here gives the power architecture of RTL8772GWP, which is designed for smart UI applications. Compared to the previous series, it has more power pins to supply power for new peripheral interface. The whole system is powered in VBAT to PMU audio aux blocks, HVD to PMU, VDDIO to I/O pad cells, VDDIO 18 to MCM SRAM, V33 USB to USB HV power supply, VD33PA to RF power amplifier, VLCD to LCD SEG/COM voltage generated. For RTL8762 and 72G, the power architecture of different IC types for different application has slight difference, so please refer to the datasheet for specific details. The B-series MCU defines 3 PMU power states for various conditions. Active mode, all clock and power is turned on. All functions operate in this mode. Deep LPS mode, high-speed clock and core domain power is turned off. The CPU stops running and can be waked up by GPIO or timer. Data can be retained in retention SRAM. Power down mode, except in an always-on power domain, all clock sources and power are turned off. Power down mode can only be woken by GPIO pins. For example, the following table listed comparison of deep LPS mode and power down mode in RTL8762C. And about the detailed data of others, please refer to the corresponding datasheet. Here is the detailed specification of the power supply DC and the switching regulator characteristics of RTL8762C, for example. Please check this table before designing system power supply circuits. The following table listed DC characteristics of digital I/O in RTL8762C, for example, and please check this table before designing peripheral circuits. The B-series MCU embeds a power on reset circuit and power on sequence finite state machine to boot the system. The B-series MCU has a blackout mechanism to avoid the situation that when VBAT voltage drops suddenly in some usage conditions to induce system crash. If VBAT voltage drops below 1.68 V, the blackout signal will be sent to digital core for avoiding crash, and when voltage recovers up to 1.76 V, the blackout signal will be released. For example, power on timing diagram of RTL8762C is the figure as shown below. The B-Series MCU integrates multiple reset protections to guarantee the system is working under some operations. One is the Watchdog Timers, WDT, to ensure the system can recover from exceptions, like MCU WDT and System WDT. The other is the External Hardware Reset N pin, which is active low to trigger reset behavior, and the drive low should be longer than 100S to avoid unexpected noise on the PCB board. While external hardware reset is initialized, all D flip-flops within the chip are reset to their default values. The chip will boot up once hardware reset N pin is released. Here also gives the reset sequence when hardware reset N is triggered. For optimal power consumption and performance, B-Series MCU offers high and low frequency clocks. The high-frequency clock is generated by an external 40 MHz crystal oscillator. The low-frequency clock is generated by a 32.768 kHz per 32 kHz crystal. In normal mode, the high-frequency clock is kept running to provide clock to the CPU, Bluetooth core, and the peripheral block. B-Series MCU needs an external 40 MHz crystal to generate the system main clock. But with the help of the internal built-in capacitor, the external capacitor C1 and C2 could be replaced and the clock offset could be fine-tuned in the mass production process, saving the BOM cost, minimizing the PCB dimensions, and adding flexibility for clock fine-tuning. In low-power mode, the high-frequency clock is turned off for power saving. The 32.768 kHz per 32 kHz low-frequency clock remains on to provide clock to the RTC, real-time counter, BT core, and PMU. In addition, it has a built-in internal 32 kHz COSC used as a low-speed clock source. With runtime self-calibration algorithm and limited user environment, temperature variation of less than 1 degree Celsius per second, the BLE link could be maintained via the internal 32 kHz RC oscillator. According to the mass production calibration strategy, frequency offset calibration is processed in two cases. If the product used external capacitor which have better stability and less sensitivity to changes in ambient temperature compared to internal capacitor, you can choose to keep same capacitance settings for all PCBs for convenience. Otherwise, if the product only used internal capacitor for saving BOM cost and flexibility, it is suggested to do individual calibration for each PCB, and the frequency offset can be controlled within a small range. The startup waiting time is to ensure that the crystal oscillator has sufficient startup time. When the crystal startup time is greater than the startup waiting time set by the IC, the SW will crash. The IC crystal startup time can be set by MP tool, and the startup time is directly related to the value of crystal capacitor. The larger the crystal capacitor is, the longer time the crystal oscillator startup takes. In addition, the PCBA crystal startup time can be measured by an oscilloscope, and the detailed measure method please refer to hardware instruction. For RTL8762E and RTL8752H and RTL876 and 272G, it add the auto-detect crystal delay function which will automatically detect and fill in appropriate values to minimize power consumption. B-Series MCU has internal eFuse. The security mechanism requires to program the eFuse inside the IC during mass production. For RTL8762C and D and E and H, VBAT must be exactly 2.5 V, plus or minus 10%, when programming eFuse, while for RTL876 and 272G, VBAT must be 3V 3.6 V when programming eFuse. eFuse area can only be written once. Hence, make sure that the data to be burnt is correct before programming eFuse. As to when to write eFuse, please refer to the Security Mechanism User Guide. Some packages have internal flash such as RTL8762CJF and CKF, normally with F, while other packages such as RTL8762CJ and CK need external flash, and available flash is mentioned in Flash QVL. Bypass mode. When B-Series MCU power on or reset, if log pin is pulled low, the code in flash would be bypassed and IC would execute ROM code. External flash should be connected to SPIC interface or FMC0 interface. It could support 1-bit mode, standard SPI, 2-bit mode, dual SPI, and 4-bit mode, QSPI. If the external flash is a normal voltage flash, 3.3 V, the rise time of the power supply voltage from 1.8 V to 3.3 V should be controlled within 15 milliseconds. As the table lists, here gives the information about the supported wireless communication protocol of B-Series MCU, RTL8762C support BT 5.0 core specification, and RTL8762D for BT 5.1, RTL8762E for BT 5.2, RTL8752H and RTL876 and 2/7 both for BT 5.3. RTL8762E, RTL8752H and RTL876 and 2/7 add the 2.4G proprietary feature. Besides, only RTL8752H and RTL876 and 2/7 support Zigbee/Thread function. As illustrated in figure, the Bluetooth RF transceiver is an essential component for wireless communication, consisting of both transmitter and receiver parts. The transmitter component includes a transmit mixer that converts the baseband input signal into an RF signal, ensuring optimal stability and modulation characteristics. Additionally, an integrated power amplifier, PA, is embedded within the chip to boost signal strength. The power amplifier integrated in the chip can provide up to maximum 4 dBm, 7.5 dBm or 14 dBm depends on package type in the ISM band. On the receiving end, a low noise amplifier, LNA, is placed in front of the receiver to amplify weak RF signals to the desired level without significantly raising noise levels. The receive mixer processes the RF signal as input and generates an intermediate frequency signal as output, which is then routed along the if path to the demodulator for decoding. And the receive sensitivity could reach to -97 dBm in BLE1M and -94 dBm in BLE2M. To achieve efficient power transmission from RFIO to the antenna, a matching circuit is required. A return loss greater than 10 dB means that 90% of the power is transmitted to the antenna. 3 components are used for matching the IC RF trace and 3 components are used for matching the antenna. The purpose is to obtain 50 ohm input impedance for both ZIN1 and ZIN2. The 22 PF capacitor for DC blocking may be optional only if the chosen antenna is a PCB antenna or chip antenna. The chosen value for antenna matching depends on the design. Sometimes, antenna matching can be achieved by using only 2 components. However, the space for 3 components should be reserved, so fine-tuning is allowed to be performed at the later stage of the design. The matching network in IC RF trace is also designed for harmonic suppression. It is strongly recommended to follow Realtek HDK instructions and choose the exact same products as those in QVL. Otherwise, the performance cannot be guaranteed. The design of antenna is crucial for the RF performance of the final product. Although the PCB antenna occupies a large area, it has the advantage of low cost, easy production, and sufficient wireless communication distance, etc. For the PCB antenna, there is trade-off between size and performance of antenna. Small antennas and large bandwidth, high-quality performance is difficult to be achieved at the same time. Therefore, the clearance area of the antenna is an importance factor and is highly recommended to refer to the following pictures. The clearance area means that no other component is allowed to be placed except antenna itself. In the 4 different designs shown in Fig A, Fig ED, Fig A has the best performance because the design deletes the redundant GND area to ensure sufficient clearance area. When allowed clearance area is not large enough, refer to Fig EC. Although the antenna length is about 1/4 wavelength, the performance and bandwidth are also be limited. According to experience, all metal should be prohibited from being placed in the clearance area, otherwise, the antenna performance will be greatly disturbed. Although Fig ED satisfies the requirements above, its antenna performance is not as good as the one in Fig A. The reason is that the GND plane is located right in the direction of the antenna radiation, which influences the antenna performance. B-series MCU has 3 types of I/O pad. Digital I/O only used for digital signal, supports all functions in pin mux table. Analog/digital I/O supports connecting to external 32.768 kHz crystal and all digital I/O functions. Supports ADC, including aux-ADC and audio ADC, and all digital I/O functions. Audio ADC was dedicated for the microphone application, fixed at P2_6, P2_7. Special/digital I/O shared by MICBIAs, it could be switched to digital mode and supports all digital I/O functions. All I/Os support the wake-up function. Different resistors can be connected to pull up and pull down to achieve strong pull and weak pull. For more detailed information about GPIO index, driving current, pull resistor, default pull state, fixed function, please refer to the corresponding I/O pin_information in HDK. Incorrect setting of pad in DLPS mode would cause abnormal current leakage. Please refer to the following figure as example. If pad is set to output function based on the external circuits, the state could be set to output high, input pull up, output low or input pull down. And for input function, according to the pad input state, if high Z, it should be set to input pull down or pull up as needed. While if the input voltage is between 0.3 VDDIO and 0.7 VDDIO, the pad should be set to pull none and shut down mode, which will disable the wake-up function to prevent false triggering, else input pull none is enough. Additional attention should be paid under the following circumstances. There must not be any voltage drop placed on the audio ADC pin before the IC is powered. If IC produces a VDDIO pin, the voltage on VDDIO must not exceed the voltage on VBAT. The voltage drop placed on the I/O pin must not exceed 3.63 V. 1.2 V and 1.8 V output of IC is only available for internal use, any external connection is not allowed. GPIO to pad mapping has multiplexing. For detailed information refer to I/O pin_information. Some I/O pins have default functions while powered on. For detailed information refer to I/O pin_information. Then is the part of peripheral. Here we mainly introduce the points that need attention in circuit design related to common peripheral applications, rather than usage or spec aspects. First is the audio part. B-series MCU has built-in mic bias adjustable output with adjustable step voltage to supply power to microphone. Detailed information about voltage range is contained in the datasheet. This pin needs a bypass capacitor when used as mic bias. In addition, mic bias pin can be used as digital I/O in applications where mic bias output is not required. For analog mic, it is suggested that differential circuits should be used in microphone application to avoid common mode noise at PCB. And here gives the connection circuit of analog mic. P2_7 is mic_P, P2_6 is mic_N, and these two signal ports could not be swapped. To obtain better audio performance, capacitances of X5 R type should be used for mic_P/mic_NDC blocking. Besides, the resistance of R12 and R13 should be equal to the output impedance of MEMS mic, otherwise, it will seriously affect the performance of microphone. For digital mic, any I/O can be used to connect to digital mic CLK and data pin, because B-series MCU can use PinMux function to switch DMIC interface to any I/O pin in IC. B-series MCU provides a built-in, maximum 8 channels, 12 bits, 400 kbps aux for external analog signal sensing and internal VBAT voltage monitoring. The functional block is shown in figure. Supports single-ended input mode and differential input mode to sample, and bypass mode and divide mode for different input voltage range. For divide mode, the input range is 0V 3.3V, while for bypass mode is 0V 0.9V. As the figure shown, in bypass mode, the internal switch SW1 is closed while SW2 is open. The voltage of ADC pin will connect to internal sample circuit directly. Thus the maximum input voltage cannot exceed 0.9V in this mode. If the input voltage exceeds the ADC range, IC will be damaged. While in divide mode, the internal switch SW1 is open and SW2 is closed, so the voltage will be divided by the internal resistor RA and RB. Aux full scale is 3.3V in this mode. When the input voltage is between 3.3V and 3.6V, the ADC value may be out of range, causing measurement error. The internal load impedance of ADC pin is about 500 ohm. In the continuous sampling mode, the resistance of RA plus RB will be affected by the sampling rate. The higher the sampling rate is, the lower the resistance is. And we suggest this strategy to choose working mode of AUX ADC. When the test voltage is smaller than 0.9V, bypass mode will be fine. When test voltage is between 0.9V and 3.3V, choose divide mode. And if test voltage is greater than 3.3V, the external voltage divider circuit is needed to adjust the voltage to below 0.9V, then use the bypass mode to sample. For IR LED and key matrix circuits design, the following points need attention. To avoid the supply voltage drop to below 1.8V caused by current draw when IR LED is turned on, which may lead to IC reboot, a 22 microfarad filter capacitor is essential. When selecting control signal pins for IR LED drivers, pay attention to the default state of GPIO pins, avoid default pull-up or output high, which may lead to unexpected activation. And this principle also applies to RGB LED control pin selection. Please refer to I/O pin information. For key matrix circuit, the row is set as input with internal pull resistor, and column is set as output, which is in open drain mode. For one-layer PCBA applications, where carbon film traces are used to keypad interconnects, it is necessary to ensure the trace resistance below 5 ohm to prevent voltage level misdetection. To prevent ghost key issue, the placement of 3 combination keys within a 2x2 key matrix should be avoided. As the table shown, these documents are involved in HDK, the reference design, reference RBOM, IC footprint, and I/O pin information. The reference design is for schematic design, the reference RBOM is for critical components selection, the IC footprint reference is for drawing package work in layout, and the I/O pin information, which lists the detailed information about default pull state, driving current, GPIO index and specific function of I/O pins for peripheral interface circuits design. Besides, after customer finish their draft of product design, we will help to double-check the customer's design and provide specific suggestion based on it. And the schematic and layout checklists documents are the review feedback of customer's product design. As the figure shown, the schematic design should follow the RTLXXX_reference_design.dsn in HDK document, which includes MCU, crystal, PI matching circuit, power bypass capacitor, switching regulator circuit and test point. It also includes the recommended peripheral circuits such as microphone circuits, DAC circuit, SD NAND flash circuits, USB connector for customer reference. The spec of critical components such as crystal, inductor and capacitor must meet the requirements in RTLXXX_reference_BOM.XLS in HDK document. For inductor, accept the value. We need to check that the self-resonant frequency must be greater than 40 MHz and the rated current must be greater than 0.5 A. By the way, the rated current of inductor includes saturation current and temperature rise current. Some datasheet of inductor may not list the value of rated current directly. Instead of the figures of saturation current and temperature rise current is shown. For crystal, accept the frequency value and load capacitance, the frequency tolerance, frequency stability, drive level equivalent series resistance and insulation resistance are also need to be checked to meet the requirements. To complete a PCB layout design, first, the position of MCU and antenna should be decided according to the product requirements. Then follow the order below to arrange the components. The higher priority indicates that the component should be close to MCU. First is DC/DC circuit components. Second is VBAT/HVD bypass capacitor. Third is RF circuit components. Fourth is 40 MHz crystal. Fifth is RF VDD bypass capacitor. Last is other bypass capacitors. As there are many points that need attention in the layout work, so here we'll briefly introduce a few important rules for example, and the detailed design guide for layout should refer to the hardware instruction document in HDK. First is the DC/DC converter circuit section. The layout and routing of it determine whether the converter can output stable voltage for digital core and RF circuits, which is critical to the performance. As shown in the figure, the switching regulator power pin LX goes through the 2.2 A inductor and a 4.7 microfarad capacitor to form a stable, low-noise power source. It is strictly prohibited to pull out the power without going through the 4.7 microfarad capacitor. The inductor and capacitor should be placed near chip to make sure the trace of the switching signal LX must be short and wide for the consideration of EMI issue, and the trace width is suggested to be at least 15 mm. The ground terminal of the 4.7 microfarad capacitor should be close to the chip's EPAD to shorten the ground loop. If the space is sufficient, place more ground via around the ground pin of 4.7 microfarad capacitor. Then here is the RF circuits, which determines the RF performance. As the figure shown, first, the RF trace must be straight and the trace width and spacing must obtain 50 ohm impedance, which may need the PCBA manufacturer's help to calculate the accurate value based on the PCBA's stack-up, and a complete GND array should be placed between RF trace. For RF matching capacitors, ground vias should connect to ground layer directly, instead of top layer. Besides, there should be no other signal traces that goes through the reference layer under the RF trace area. For antenna, the reference ground should return to IC EPAD as soon as possible, and the clearance area is essential. Here is a brief introduction to the debug process. First of all, for download, debug and test function in mass production, designers need to reserve the following test points while designing PCBs: VBAT, GND, log, UART_TX/RX, and HW_RST_N. When encountering problems, you can perform basic checks in the following order. Power on the IC after P0_3 is pulled low. Flash bypass. Check the correctness of VBAT/VDDIO voltages, which should be within the range specified in the datasheet. Check whether the 1.2 V of SWR has an output and the voltage is correct or not. Check whether the 40 MHz crystal has started to oscillate or not. Check whether the log UART has an output or not. Check whether the UART is available or not. Check whether the external flash is working properly or not.